Today our lecture is about some complex topics in algorithms and data structure. So we've covered how to calculate some time complexity of algorithms. We covered sorting algorithms, some dynamic programming algorithms like Dijkstra, minimum spanning tree, maximum flow, DFS, DFS. So we've covered them, but we've never talked about some algorithms that cannot be fast. We had Fibonacci sequence. We tried recursive algorithm that worked exponentially, but then we used dynamic programming to solve it in linear time, and then we used some arranging powers to calculate it in even logarithmic time, etc. So sometimes you have a question: what is n in this task? Yes. So when we measure the time complexity, the memory complexity, you can have the question: what is n? What is the number of what we base our calculations? So today we will talk about how it is done properly, so all the mathematical foundation, and also we will talk about formalization of computer, of anything that can be done using computers. So let's dive in. So the first topic will be Turing machine. And everything will be about Turing machines so far. So, what is a Turing machine? So, we are given some infinite tape. On this infinite tape, we can have some letters. So letters come from the finite alphabet. So this alphabet is finite. This symbol, lambda, is empty symbol. It means nothing is written here. So it's like empty symbol. Other symbols mean something. Then we have an alphabet of states. So our machine has some states in which it can be. So it is also finite set. So there are like some numbers. And infinite tape is filled with symbols from A, but only finite number of symbols are not lambda symbols. So other symbols are all lambda, and some finite subset of the symbols is non-lambda. So this is just a set. Now we will say, okay, let's say that this is the first state. So the state at which the machine starts working, and Q0 is the ending state. It means if machine reached Q0, it stops. So we know, oh, machine stopped calculation. So for example, if you launch some program, you do something, you ask it to, like for example, to make a payment. You need some message successful or something like that to know that the transaction is over. So everything is finalized. So it is the same. So it is like a message that the machine finished its work. So the result of the machine, what is output of the machine, is the sequence of the symbols that are not lambda. So all meaningful symbols on the tape after machine stopped. So you wrote something, you started the machine, it moved something, changed some numbers, worked on that, and then stopped. Now you read what is written there, and this is the output of the machine. So that's how it works. Okay? understand? So it's like a simple object. So this is the starting configuration. So the first state we are in, and we are looking at the first left non-lambda symbol. So there might be several of them, but because it is finite number of non-lambda symbols, you can always find the first one. So we are looking at the first one, and this is input. Then we have configuration. So when machine is working, you have time steps. So at time number 1, it's looking like that. At time number 2, it's done something. At time number 3, it's done something. So the configuration of the machine changes. So at any point, you have some configuration looking like that. So there are some symbols before. Now the machine is looking at that symbol in this state, and there are symbols after. So machine can move at any point one cell left, one cell right, or be at the same place. So there are only 3 movements for machine. So it can either move one cell left, one cell right, or stay at the same cell. And also it can change state. So it can change these states. Okay? So actions, what I'm talking about is going right, left, or stay at the same state. And we write them like this. So we say, at the state Qi, looking at the symbol AI, I'm doing next command. I'm changing to state Qj. It might be the same state. It's not restricted. At any state, you can move to any state. Write any letter, so you can keep the same letter. You can write the same letter AI, or maybe replace the letter. It's up to you. And then do the action, so move right, left, or stay at the same place. Okay. Does it make sense? Now, let's see an example. Let's say that we have an alphabet consisting of 3 symbols, lambda, which always must be in the alphabet, and then 2 meaningful symbols that are 0 and 1. So we represent number in which system? Binary, of course, it is binary system. So we have a binary numerical system. We represent any number as a binary number, and the task is multiply the number by 2. So when I have a number in binary system, what does it mean to multiply by 2? No, not should. Think more creatively.
numbers?
No. So if I have binary number, what will it look like when it's multiplied by 2? 0 at the end, and that's all. Because this is infinite tape. You don't need to shift anything. It can just stay at the same place because there are infinite number of cells after the number. You can just write 0 to the end. Add new 0, and that's all. So, what we have in the plan? So, in the beginning, we are looking at the first left symbol. But where we write the 0? At the last point. Yes, so first thing, we need to move right. So we don't change any digits. We move right until what happens? No, we can move anywhere. We are not restricted of movement. But what changes that machine sees that we reach the end? It sees lambda, of course. So let's write the command. So Q1 is the first state. Yes? So if it sees 0, does it change 0? if it sees 1, the same just here will have 1. So it replicates the same thing that it sees until it reaches lambda. So when it reaches lambda, what should it write? 0. So it should write 0. But when the machine ends, it's preferable that it also looks at the top left, the leftmost symbol. So it should go back. Why do we do this? So you know about the functions already in programming. So you call one function, you call the next function, you call third function, and you can call inside one function another function. So you want machine to be at the same place it started. So it changes the argument, it changes the output, but you always know where is the machine. So if you have this agreement that machine is always looking at the leftmost character, non-lambda character, then we just need to do this, and everything will be easier. So we switch to another state, because Q1 will always move to the right, and we need to go to the left. So we need another state and go left. So this state will always go left until what happens? Until it sees lambda, because then it went too much left. Yes? So when it sees lambda, it means it before saw 0 and 1, so it needs to go back right 1. So we need to go back right. We write lambda as well because we don't change the number. Q1 changed the number. Q2 doesn't change the number. It just moves left. And what should be here? Exactly. It should stop. And that's the code of our Turing machine. So multiplication by 2 can be done with this much code. Okay? Does it make sense? Okay, so the interesting part, it is not like the easiest thing, the machine, the Turing machine. I chose specifically multiplication by 2 because it just adds 1 0. So you can easily do multiplication by 4, by 8, but the number of states will increase because you need to count how many zeros you add. The only way to count from Turing machine is to change the states. If it is a fixed number. If you want to make like program that will perform multiplication of two numbers, so you want multiplication of two numbers, then it doesn't It doesn't have these states to count. It has numbers. It is what's written on the tape. How do we multiply A by B? Yeah. How do we multiply A by B? So the numbers are written in binary form. How do we multiply two binary numbers? So the easiest way is to write a program that adds one number to another. Yes? Can we do this? Yeah. So we can add number to another. We need addition. So we have a program that adds one number to another. Then we add one number to itself, the number of times another number. So we need another program that can subtract 1. So we need a program that can add one, subtract one. So we need some easy programs. We write them, then we combine them to reach just multiplication. So in order to do multiplication, we need several programs on top of each other, because it's harder. However, there is another way that you can use. For example, we say that we have only one tape. Yes? What if we could have 3 tapes in parallel? It is proven that this situation is the same as having one tape. So you can just write first number on the first tape, second number on the second tape, and on the third tape you can write the answer. Yes? So you just multiply using the usual form. So you write one number, then add another number, and so on. Shift it to some places. And it works faster. So there are like cheat codes that we can use. Okay. However, it's not over with Turing machines. So the sequence of configurations is produced by actions that we wrote. The machine, when it reaches the ending state, we say it halts. So it's just a definition. When the machine halts, when it reached Q0. Okay. Otherwise, machine doesn't stop and works forever. So that's the total number of the configurations in the sequence that machine reached before halting is called the time of working. So what is the time? Is the number of steps that machine took. So even those that when it doesn't change the place, so if it uses E, not going other step, it changes the state. So we still call it one more step. So the number of steps machine went from the start till the end is the time of our complexity. Yes. So this is time complexity of the task, of the given task. So we already know what is time. So it's very different from the things we had previously. Yes, we thought, oh, what is the number of operations? But we had like operations additions, we had operations multiplications. We didn't know what is their relationship. So is the time of addition greater than time of multiplication or vice versa? Maybe they're the same. We didn't think about it. But here, we exactly count every step. So here, everything is precisely. Okay. So we have precise amount, estimation of the time. So now we can talk about time complexity, but how to measure time complexity of some task. So you have some Turing machine, and you need to estimate its time complexity based on what number. So you will give this number, and it will work so much steps. You will give another number, it will work another number of steps. So you need some estimation. So we will base this estimation on the length of the input. So we are given the length of the input. We have the input, so we can count the length, the number of non-lambda symbols. So we can count it. Next, if the working time of algorithm A that solves our task with the length of n is bounded by a polynomial of n, then this machine works in polynomial time. This is the definition. So now you know what is the polynomial time complexity. It is when, based on the length of the input, the number of steps is bounded by the polynomial of this number. Okay, so let's see the difference. We present the number in which system? Binary. So let's say we have number n. What is the length? What is the length of the number n? In binary system. Yes. Logarithm base 2 of n. This is the length of our number. So now, the number of steps must be polynomial of the logarithm of n, not of n itself. Because if it is polynomial of n, then this will be how to get from logarithm n. Of course, it will be exponent. You need to raise 2 to the power of logarithm, and then you will get n. So if it is polynomial of n, it means it is exponential algorithm. We need polynomial of logarithm of n. So that's the trick. Do you remember the school algorithm how to find if the number is prime? So you took the number n and then tried to divide it by numbers from 2 to square root of n. So if you got integer number, then it is not prime. If you didn't get integer number, it is prime. So what is the number of steps? Square root of n. So what is the square root of n in terms of logarithm? It will be 2 to the power of length. It will give us n. But we will need to take square root. What is the power of, what is the square root? What is this power? Half, yes. So this is the time complexity of that algorithm. So you see, it is exponential algorithm. Sub-exponential, but exponential algorithm. So even though we go through the numbers from 1 to square root of n, which is less than n, we don't call this algorithm linear. We can have the time complexity correctly. It is exponential. Do you get it now? The difference between n as a number and the length of the input. But why, when we said something about the sorting of arrays, we counted all from n and set it polynomial? Because the length of the input is the length of the number times how many numbers there are in array. And the amount of numbers in the array is our n. That's why we could say big O of n. Why didn't we big O of n squared? Big O of n log n. Big O hid from us this logarithm of the length of the number. So logarithm of the largest number. This is hidden inside of big O. That's why we use big O. Not because we want to use it, but because it is inside. It should be there. Some constants, they are always there. Okay?
If you store it bounded by some number?
Because if you store it in the array of type int, 32 bits, you already know 32 is the length of the number. Then you multiply by the number of numbers, which is n, so 32n. This is the length of your input, and then you base your calculations on this length. So this is the difference between counting just number and many numbers. Okay. Do we get it? Okay. So, okay, finding minimum. Let's say that we have some example of algorithm that finds minimum. So what we do? We assign minimum as the first element, and then go from first element till the last, and we look if array at this point is less than minimum, then minimum we change. So how many operations we have? Well, check and reassignment. So 2 at each step, at maximum 2 at each step, so it takes us 2n operations, where n is the length of array. So it is the estimation of the length of input. That's why we call this algorithm linear. And you remember that I told you, if we count the Fibonacci and Fibonacci number, I gave you logarithmic time algorithm. But if you write n in binary system, you write it in logarithm length. So it is actually linear algorithm. That algorithm that raises matrix to some power in fast method. Yes, so we have fast method of raising to the sum power. So this algorithm actually is linear algorithm. And others are exponential. So, now, let's move to another. So this is the hardest topic. Okay, let's take a look at this. So we already covered what is polynomial time algorithm. But what is non-deterministic polynomial algorithm? So let's say that we do not fix the starting state. Q1 was the starting state. Now let's not fix Q1. Let's have different states as a starting state. And imagine that from one of the states, given the input, you solve this problem in polynomial time. Then this task is called non-deterministic polynomial. And deterministic means we don't know from which state we need to start in order to solve this problem in polynomial time. So we don't know the state. But there is a state inside the machine that allows us to solve this in polynomial time. So if we change the input, the state will also change. So we don't know from which state. For any different input, it will be different starting state that will solve it in polynomial time. So we call that non-deterministic polynomial. Okay? Do you know any example of computers that can solve non-deterministic tasks? Do you know any example of computers that can solve in non-deterministic way? Okay, you don't. It is quantum computers. They cannot solve any non-deterministic polynomial algorithm, but it can solve some of them. There are some tasks you can develop algorithm for quantum computer that can solve like all the states at the same time. So it can go from all the states at the same time. That's how it works. Because what we have entanglement in quantum computers. So small particles, if you try to determine their velocity, the exact position is undetermined, and vice versa. So there are some things that, because of superposition, each small particle can be at the same time at continuous of states. So if you design your algorithm such way that going through all the states you can calculate the answer, so here you go, you can solve some problems. So quantum computers can solve some problems very quickly because they do this in all states at the same time. So starting from all states at the same time. But usual computer cannot do this. So let's give another example of non-deterministic polynomial definition. So this one definition is very hard to check, but because you need to solve it for any task, etc. So we can have another definition. So another definition is, let's have one task, let's say P. We have some input I, and we are given some hint to this problem. And the length of the hint is polynomial of the length of the input. So it's not like exponential of the input. It's polynomial of the input. And we have some hint. If we can construct algorithm that works in polynomial time and can say, oh, this is the answer, this is correct, or this is incorrect. So only answers yes or no. If we can construct algorithm that can give us answers yes or no in polynomial time, we call this task non-deterministic polynomial. Okay. So what can we tell? All polynomial tasks must be non-deterministic polynomial. Because you just don't give the hint and solve the problem. And you can say yes or no without a hint. Yes? But what is the hint for, let's say, this task, for checking for prime number? So let's say that we wrote the number n, and then we wrote its divisor, its largest divisor. Okay, smallest divisor greater than 1. Let's say like that. So we write hint as the smallest divisor of n greater than 1. Can we check then if it is prime or not?
Yes.
No. The smallest divisor greater than 1 can be n itself. Then it is prime. So if we have two same numbers, then it is prime. If we have this number and the hint is some number less than n, then it is not prime, yes? So checking is very easy. So given the hint, we can solve this problem quickly. So it is non-deterministic polynomial task. Okay. Let's take a look at another problem. Okay. We are given undirected graph G with vertices V and E. We call a cycle a Hamiltonian cycle that is a simple cycle that contains each of the vertices exactly once. So it is a cycle that goes through all the vertices without revisiting any vertex. So we start from here, go along this like this, and come back here. And that's all. So this is the Hamiltonian cycle. So this task is non-deterministic polynomial task. How can we prove this? So we need some problem that, given the input and the hint and can say yes or no in polynomial time. If I write so for example, I will write the input in the way, so I will have all edges, so E1, E2, EM. These are the edges of the graph. I can describe the graph using the edges. So how do I do this? E will be VI1, VI2. So the pair of vertices, yes? So I describe the graph like this. I can describe it. So the length of it is O of M. Yes? So the length of it is O of M. Okay. We need to find a Hamiltonian cycle, so the graph must have at least one cycle, yes? I mean, it doesn't make sense to check the graph that doesn't have cycles, that include all the vertices. So what is the length of the simple cycle that includes all the vertices? N, where N is the number of vertices. So if I write the number of vertices as N, so the smallest number of edges that we're interested in is N. So if the length is smaller than N, we don't care. Because this graph will definitely not have Hamiltonian cycle. It doesn't have a simple cycle that includes all the vertices, what we care about. So we know, in order for this problem to have any solutions, M must be greater or equal than N. Yes? Where N is the number of vertices. So now, what is my hint? So the hint is the order in which I want to go through this cycle. Is the order of vertices in the answer. So if I write V1, V2, V3, V4, like that, in this direction in which I can go, if I write vertices in order in which they appear in Hamiltonian cycle. So, can I check whether it is a Hamiltonian cycle? Well, I need to check that all vertices are distinct. This is O of n. Let's say O of n squared. If we check them pairwise, doesn't matter. It is still polynomial. Then, I need to check that if I have them in order. So, it is VG1, VG2, VG3, etc. VGn and VG1 again will be yes. So we will not write VG1. We know that it should go to VG1. Okay. So what I need to check if this pair is edge. If this is edge and next edge, next edge, I just need to find them in this list. So this check is, of course, polynomial. Yes? I just take this pair and check. So I will lose like m operations for each pair. Yes? I need m operations to check each pair. And I have n pairs and m operations. Yes? So then I wanted also to check if they are all different. So it will be n squared. So this is the complexity. Now, m is greater or equal than n. So instead of n, I can write everywhere m. And this will be in the worst case scenario, yes? of m squared, which is polynomial. So I proved Hamiltonian cycle is non-deterministic polynomial problem. It can be solved using non-deterministic polynomial algorithm. So this problem can be solved using such algorithm. I constructed the algorithm. No, you can solve, but not in polynomial time, maybe in polynomial time. We don't specify it. In definition of NP problem, we don't specify, can we solve this problem in polynomial time or not? Only can we solve with a hint in polynomial time. If yes, then we call this task non-deterministic polynomial. Because all polynomial tasks are non-deterministic polynomial. If you can solve the task in polynomial time, you just solve it in polynomial time, and that's all. You already have the algorithm. You don't need to use the hint. You just solve it. So, but for some tasks, you need a hint to solve in polynomial time. So without hint, it will take you much more time. Okay? Because the number of orderings, if we have n vertices, the number of orderings is n factorial. So the baseline algorithm, the brute force algorithm, is not even exponential. It is factorial algorithm. But it is not deterministic polynomial still. Okay. Do we have any questions on Hamiltonian cycle? Okay, now let's talk about reduction. So let's say that we have problems 1 and problems 2. Значит, problem 1 is one task, problem 2 is another task. They are like different tasks. Very different. Now, let L1 be algorithm that can translate input to P1 to the input to P2. We don't know yet that it works or not. We just say we can translate one input to another input. Then L2 be algorithm that translates output of task P2 to the output of task P1. So, if for every valid input I1 to task P1, the result of this is the same result we would get as the answer to P1 given the input I1. So we translate it to the input of P2, solve problem P2, translate the output back, and if the answer is the same answer we would get if we just solved the problem 1, we can say that we can reduce P1 to P2. So there are some ways, for example, to use this. It's not like very complicated. Yes? Changes. For example, let's say you are given some task. Find k order statistics. So you can use quick sort, modified quick sort, that can find you k order statistics in some steps. Or you can just sort the array and look at the kth element. So what you do? You translate your problem to another problem, just sorting. And then you sort, and then you translate output back. So instead of using all the numbers, you just take the kth number from the sorted algorithm and put it as output. So this is the translation. Yeah, so we have one task and we use this task to solve another task. And the translation is preparing the input so that this task can do this, and then preparing the output that this will be the answer of our task. So, if both L1 and L2, the translation algorithms, are polynomial time, then we call that we can translate P1 to P2 in polynomial reduced time. Yes, so the time of translation reduction is polynomial. Then, what we can say? We can say that the time complexity of P1 cannot be harder than time complexity of P2. Okay? If the time complexity of L1 and L2 is less than time complexity of P2, then we can say P1 is not harder than P2. That's the whole point. So we need some formalization to use other tasks. So we proved that we have one non-deterministic polynomial task, which is Hamiltonian cycle. We already know one task. Now, what is NP completeness? So NP complete problem. So we call it NPC, non-person character, I guess. So this is NP complete task. It means any NP task can be reduced in polynomial time to this task. So it means this is the hardest task that is non-deterministic polynomial. Any task that is non-deterministic polynomial can be translated, so reduced in polynomial time to NP complete task. We can solve it and get the answer of the task itself. So what does it mean? Why do we need NP complete tasks? So if you heard, we have the problem. So we have polynomial time algorithms. And we have non-deterministic polynomial time algorithms. The question is, do they represent the same set of problems or not? Because we know that P is a part of NP. All polynomial tasks are non-deterministic polynomial. But is it true that all non-deterministic polynomial are polynomial time? We don't know it yet. It is open problem. It is open problem like more than 50 years. So nobody solved this problem yet. And there is a price of 1 million if you solve it positively. So if you say that they are equal, you'll get 1 million. If you prove they are not equal, you will not get 1 million. But you will get like, I don't remember, $200-something thousand. One scientist made his fund for those who prove that they are not equal. He said, I will pay because it will solve a lot of problems in my life. Just prove it. Yes, so nobody proved it yet. Because this task is very hard. Like, the hardest task to explain. Okay, so let's talk about Boolean algebra. So we have several operations in Boolean algebra. So we have disjunction. So given A, B, and A or B, we will have 0, 0 will give us 0, 0, 1, 1, 0, and 1, 1. Okay, that one is good. Then we have A, B, and A and B. Okay, here 0, 0, 0, 1, 1, 0, and 1, 1, 1. And now we these are the basic operations that we can have, and for those operations, actually, if we use all those operations, we can represent any Boolean function using them. So we can represent any Boolean function. Let's say we want to represent 0. Then we take x and not x. This will be always equal to 0. If we take x or not x, it will be always equal to 1. So we represented 0 and 1, and we can represent any function using these three operations. So in order to represent it, we have conjunctive normal form. So what is conjunctive normal form? So we have sums S1 x I1 in the power sigma I1, or x I2 in the power sigma I2, or let's say this is G, or x ij and sigma ij. So this is some numbers, yes? What is power? It's that. So x to the power sigma will be x if sigma is 1, or not x if sigma is 0. So it's just to represent the whole thing. Okay. So let's say we have this sum. We have many of those sums, and we use conjunction to multiply them, because it is the same as multiplication, yes? So we can multiply them. So we have S1 and S2 and so on, Sn. So the question is, does it ever equal to 1? So solve the equation. Does it ever equal to 1? That's the whole problem. Okay? So this is the problem. And this problem is an NP-complete problem. This is for sure. We need to prove this is NP problem. Then we need to prove that this is NP-complete. Yes? So let's start with NP. Is this problem NP? So, if we give hint, that is the values of each of x's, that you can substitute and check, does it equal to 1 or not? Yes? You can do it easily. So you can do the checking in polynomial time. And the length of the check, of the hint, is also polynomial time, because it is the number of variables. So it is the same as the number of variables. So you have here all the variables, so the length cannot be like hugely more than the length of the input. So usually the input is huge, and the hint will be very, very short. And you just need to substitute all the values, calculate the first S1, then S2, S3, and check that all of them are equal to 1. If all of them are equal to 1, the answer is yes. If one of them is not equal to 1, the answer is no. So the checking time is polynomial. So set problem, satisfiability problem, is NP problem, because we can construct the hint of polynomial length that can be checked in polynomial time. Okay, so this is a good problem. Now, the next part will be a little bit complicated, but we'll try to simplify it as much as possible. So we will translate any given NP task to satisfiability problem, and we will use Hooke-Levin's theory to prove that this is the case. Somebody? Yes, no, they have the computer here. Okay, so let A be task P1 that is non-deterministic polynomial. So we have an algorithm that can check for this task given the input and hint if this is yes or no problem. Yes, so it is yes, it is correct, or no, it is incorrect. So we have input and we have hint. So we can design an algorithm that works in polynomial time. Yes? So the Hooke-Levin's theorem said, let's write all steps of Turing machine that works on that task P1 as satisfiability problem. And if it is satisfied, what does it mean? It reaches the final state and says 1, so it says yes, then the hint is true, and our satisfiability also solves this problem. It solves that the hint is true. So what do we do? Okay. We put Boolean values Qik that are equal to 1 only when A is in the state Qk at the step I. So what do we have? We have Q I step. So 1, Q I 2, etc. Q I m, Q I 0. So these are the states of our algorithm, of our Turing machine that solves problem P1. These are the states. We need to make sure that at any point only one of them is equal to 1. Yes? Only one of them is equal to 1. So what do we need? We need to take OR of all of them. And if it is equal to 1, then one of them is equal to 1. Then we need to make sure that at this point, only one of them should be equal to 1. So we will make what? Let's see what's that. So we will make those things, all those sums that must be equal to 1. What does it mean? So the machine should be at step I at state j. If I do not, from 1, this variable will change to 0. In order for this thing to be satisfied, so to be equal to 1, this thing must be equal to 1. When not is equal to 1? When this is 0. So we will put all the pairs of this state. So let's say that Qij must be 1 and others must be 0. So we will put for first thing will be Qi1 or Qi2 or etc. Qij etc. Qi0 as one of the s's, s1 or s2, doesn't matter. Next, I will multiply it by Qij not or Qi1 not to make sure that only one of them is equal to 1. So this is satisfied. This must be equal to 1. So one of them is 1. If two of them are 1, they both will turn into 0, and it will be not satisfied. So then we will have Qij not, or not Qi2, and so on. For all pairs of distinct states, we'll have this. Then we need to check that at each step the head is exactly at one position. So we have here Boolean values Hij that are equal to 1 only when the automata at the step I in the position j of the tape. Yes? So when algorithm works, the machine looks at only one cell. We can number them, numerate them, and say, okay, Hij is equal to 1 if the machine at step I looks at this cell, and equal to 0 if it doesn't look at this cell. So we also need to make sure that only one of them is equal to 1. So we do the same thing. Just replace Q with H, and you will have the same thing. So we also make sure that one of them is equal to 1, and only one of them is equal to 1. Next, we have more complicated thing, SIJL. These values are equal to 1 only when at step I, the symbol in the square J is symbol number SL. So you remember we wrote here those things, yes? So at each cell there should be only one symbol, not two at the same time, only one symbol. So the same thing, we need to make sure that those have only one, and the others are zeros. So if I fixate I and j among all else, only one should be equal to 1, others should be equal to 0. Oh, this I told this thing. So I fixate ij, so among all of them, only 1 is equal to 1, and if I fixate I and j, among all of them, only 1 is equal to 1. And so we make sure with the same approach. So this is configuration, that we make sure that at any step we can encode the configuration of Turing machine. So we encoded the Turing machine at any step. Because we are given the input, we know the input to the task. We can modulate the actions of the Turing machine, and we can write for each step what we will have. So it will be very, very long input. Very, very long. Doesn't it? Next, we need to make sure that we have changes from one comment to another comment. So how do we do this? So we put, based on x, we put -1, 1, or 0, meaning if it changes to left, to right, or stays at the same place. So here we will write y, which is this. Here, you see, y. So what do we do? So at the step I and state k, being at the position at the step I and looking at the cell j and seeing symbol L at this step thing, we need to change to next state. Okay. Then we need to write another symbol, and we need to move the head accordingly to left, right, or being in the same place. So these three formulas make sure that we change. So they are all equal to 1. So in order for this thing to be equal to 1, this must be equal to 1. So that's how we make sure that we swap to the new exactly one state. We write exactly one specific symbol, and we change the position to exactly specified position. So that's how we encode our task. So the hint is accepted for task P1 on input I only when the constructed CNF is satisfiable. So only if we reach the end of this Turing machine, if it holds and says yes, then we have this. So the reduction is polynomial as the algorithm A is polynomial. Let's discuss this. So what does it mean? We have a polynomial algorithm, yes, that works on this problem, polynomial time. The number of states of the algorithm is fixated. It does not depend on the length of the input. It just depends on problem. So we have problem P1. We have algorithm that checks the hint on this input in polynomial time. So this algorithm is fixated. We already fixed it. So it does not depend on the length of the input. The number of states, the whole table of transitions is fixated. So those formulas are already like that. So we don't have like, even though we have many states, the numbers is constant. Now, the number of steps, because we need those equations how many times? I. This I changes, yes? So we write for each I of these equations, then we write for next I, the next I, the next I. What is the number of I's? This is the number of steps the algorithm works to check the hint. But we said, because the problem is NP, non-deterministic polynomial, and we are checking the hint, the algorithm should work in polynomial time. So the number of steps is polynomial. So the number of those equations is polynomial. That's why we say the reduction is polynomial time. Now we proved that SAT, satisfiability, is indeed NP complete program. Okay. So this is a very hard problem, and this was the first theorem to be proven. And then all other theorems were much easier to be proved because you just reduce to SAT to that problem. So if you can reduce satisfiability to another problem, then this problem is also NP complete. Because for SAT we proved that any NP problem can be reduced to SAT. But after that, we just need to prove that SAT is reducible to one problem, and that's all. So if we can solve using another algorithm, SAT, and this algorithm is also NP, then it is NP complete. So other steps will be much easier. So the first step was very hard, and they did it like that, but other steps are much easier. Let's take a look. So other NP complete problems. The first problem is to find clique. So what is the clique? Let's see that we have a graph, some graph, and we already know what is complete graph. Complete graph is when any vertex is connected to any other vertex. So there are edges connecting all possible pairs of vertices. This is complete graph. So the task is, can you find, but of course you can, but what is the largest in the size of vertices, in the number of vertices, subgraph of G that is complete graph. So you want to find the largest largest complete subgraph. And this is the Clique problem. So, here with the red, we have the Clique, because A is connected to B, C, D, and E, B is connected to all others, and etc. But the whole graph is not complete. We don't have edge from I to B. If I try to add any other point, I will not get complete graph, yes, to this subgraph. But this one is also Clique, is also complete graph, but it is not the largest Clique. We want the largest one. This has 5 vertices. This has 3. This is also complete graph. This is also complete graph. Yes, not the largest. And the largest is with 5 vertices. So this task is also NP-complete. First, let's prove that this is NP task. So, hint is a list of k vertices in the Clique. Can we check that this is a complete task, complete graph? Easily. Just check that any pair of vertices are connected with edge. So just checking is the polynomial time of the hint. So we can do this easily. So this is NP task. Now, the question is it NP complete? The answer is yes. So we will write, we have SAT problem, satisfiability problem, like this. So this is our problem. Then let's create a graph with some vertices. What are the vertices? So we have those vertices. What does it mean? X, as it's here, paired with 1. What is 1? Because this is S1. S1. So 1 comes from the number of the S. So we have, this is the first. Next we have the second. So the second one will have 2 for each of the variables in the description. And the last one is T, so we write them with number T. Okay, so we have that. Yes? Now, we connect the edges in specific way. So, no 2 vertices belonging to the same clause are connected. So, xij1, 1 is not connected to xij2, 1. If they have the same number in pair, they are not connected. No variable is connected to its complement. So what does it mean? We will not have x1 I connected to not x1 j. They are not connected. So we don't have this connection. Okay? So if we have one variable as it is and another variable, this is the same variable but as complement, not value. We don't connect them. And all others are connected. So we just disconnect those things and others will be connected. Okay? So there are, oh no, not this. Okay, very good. So now we have this graph that is connected. Some vertices are connected with the edge, some vertices are not connected with the edge. We want to find Clique of which size? Of size t. The number of summon. So we have this conjunction, yes? So we know S1, S2, etc., St. So we want to find clique sized T. It will say, so if we connect these vertices in this order, so we have clique, that is, they are all connected, it says that they are not from the same clause. Yes? So, because they are not from the same clause, we selected one variable from each clause. Then, if they are connected, there are no contradictions. They are all the same. So it means if we have x1 twice in this clique, it must be the same x1. Either x1 or not x1. We don't have different ones. Okay, does it make sense? So we found some variables that are present in each of the clause in some value, in some power, yes? Now just assign this power to these variables and the problem will be satisfied. Because you found in each one of them variable that you can assign a value that it is equal to 1. Then the whole thing will become 1. You found here a variable that you can assign 1, it will become 1 the whole thing. So you found for all t of them values that you can assign to all the variables and you will get 1 as the answer. So you solved the problem. And if our algorithm will say, oh, there are no cliques of size t, it says it is not satisfiable. So there is no way to assign them some value to have them all be equal to 1. I think we need to stop here and show some examples. Yeah. Let's say that we have this function. This is CNN. So we will write vertices x1, y1, because they are from the first one. Then we will write x from 2 and not y from 2. And then we will write not x from 3 and y from 3. So how many vertices do we have? 6, yes? So we can write them in the circle. So we can write them like that, like that. So x1, let's say here y1. Here I will write x2, here I will write not y2. Y3, not x3. Yes? So now I can connect them according to my rules. I will not connect 1 to 1. I cannot do this. X and x are the same, so I can connect them, and they are from different clauses. So I cannot connect not x to any of them, because here I have not x and here I have x. I cannot connect them. Now I can connect x1 to y3, no problem. I can also connect x2 to y3, no problem. Then I can connect y1 to y3, no problem. I cannot connect not y2 to this, but I can connect this one to here, and I can connect them, and I can connect them. Then I can connect which ones?
The other ones y and 3.
This which one?
Negation x3 and y3.
Negation x3
and y3.
No.
You're right.
They're from the same clause. We cannot do this. Y1 x. Yes, correct. Okay. So we connected them. Yes? How many parentheses did we have? 3. in the power 1. Yes? It is in the power 1. So we will assign x 1. Y in the power also 1. Yes? Because it's not. If it is not, then it is the power 1. So y is equal to 1. So in this clique, we found when x is 1 and y is 1, we have the clique. Yes? So let's substitute 1 and 1. So what will we have? 1 or 1, 1 or not 1 or 1. So not 1 will be 0. So 1 or 0. 0 or 1. 1 or 1. And their multiplication, it is satisfied. So now you see how using the clique, we can solve satisfiability problem. Yes? So it is easy. The construction of the graph is very easy and the proof is also, you see that. So we want a clique of size t, the number of clauses we have. If we found it, we found the answer. And that's all. So this is the clique problem, and it is NP complete because it is P, the algorithm of checking. Just give it the clique itself and it can check. And it is NP complete because we had NP complete task polynomially reduced to it. So we need to prove if it is polynomially reduced. So how do we prove that it's polynomially reduced? So what is the number that is the length of the input? So we have xij1, xij2, etc., xijk, and t times. Yes, so we have some number of variables times t. So this is the input of CNN. So then we translate it to the problem. So we take 1 from here and 1 from other place, and we write them as the edge. So it will be square. Any pairs. Yes, because pairs, it will be like square of the size. So it's polynomial, it's still polynomial. I don't see understanding or not understanding, so let's see. So, okay. So I have, for example, from here, let's say from here. So, what is the number of edges? We have 6 vertices. So 6 vertices is the complexity of the input, because we have 6 letters in the input. We have that. So it is the length of the input. So it is not complete graph. So it has less edges than complete graph. But how many edges does complete graph have? So if we have n vertices, so we multiply it by n minus 1 and divide by 2. So the number of edges is strictly less, because there are some non-connecting for sure. Then n times n minus 1 over 2, which is all of n squared. So the length of the input, so the translation, will be done in n squared time. So it is indeed polynomially reduced. And the answer is very easy to translate back, because it will say just the numbers. So it will say you assign this variable with the number. It will say you the number, because it will say you degree. So you see the variable and the degree. So you already know what is the number you're assigning. It will be the answer. So you already have the answer. The translation part will be just to remove these things. You need to remove this, but just write the values of the variables. And just give it back, and that's all. So the answer is easily translatable. The input n squared, which is polynomial, so it is indeed a polynomially reduced task. So let's see other tasks. So there are subset sum problem. There are n non-negative integers w1, w2, etc. wn. Goal to find some subset of indices that the sum of w with these indices will be equal to some number in the input. So you have a lot of numbers and you have target, and you want to match the sum of these numbers to this target. So just select the subset of these numbers which sum is equal to this number, target number. So we want to solve this problem. So theorem SAT is reducible to subset sum problem. Proof. So let's say that we have those S1, S2, etc. Sm, and each Ci has kj literals from x1, x2, etc. Xm. Let B be equal to maximum of kj. So what do we say? We say the number of variables in each clause. Here we have 2 variables, yes? So we might have 3, 5, 10 variables in each clause. Let's select the largest number. What is the largest length of the clauses? And we will mark it as B. So B is the maximum number. Now we will rewrite our problem in base B. So it will be the numbers base B. But in usual decimal system, I'm just telling you how to understand it. So we will call Wi, each of the numbers, as B to the power of I. So we say, if I choose Wi, I will get B to the power of I. And then sum, if xi in Cj, then I raise B to the power of n plus j. So if the variable xi in Cj, then I raise this power. So I wrote those weights, now I write other weights. So those weights will be when not xi is in Cj. So I will have either every weight 0 if xi is not presented in any of them, or if xi is there, this one will have 1 in this place. If it is not xi, this one will have 1 in this place, in B, base B notation. So then we will write W like that, the target number. So the sum of all by's, because we have C1, C2, and etc. Cn. Yes? So the number, how many clauses we have. So this is the sum. And then the sum like that. It will say kj. K means the number of summons in that thing, times b to the power n plus j. So solving this problem, we just defined number is also solvable. I mean, this is this is fair. So I want to get this target. When can I get this target? When do I get this target as a number? So I need to solve this problem, choose either wi or wi plus n to match this number. Because there is no way I can get b to the power of I if I didn't choose neither of them. Only two of the weights have 1 on the place I. You see, others have 1s on the places after n. So before n we don't have 1s, we have 1s only in two i's, wi. Wi and wi plus n. So I need to select one of them to match w, big W. I need to select one of them. I cannot select two of them, because if I select two of them, what will I have? I'm sorry? I will have 2 times wi. Yes? I cannot have 2. I need only to have 1 w to the power of I. So I can only select one of them. So what does it mean? It means I need to select those in this order, and now I need to match that. What is this? It means that for each of the clauses, I selected the value of x, j. So for each of the clauses, I selected what this will be equal to, what this will be equal to, etc. So I selected their values. And because here I used diagonal method, because I will be determined, xi will be determined only once, by either wi or wi plus n. Only one of them will determine the value of xi. It's either not xi or xi. So it will be determined once, yes? And this proves that I selected the value for all of them and they do not contradict. Because if they contradict, I would have here 2. So I selected 2 of them. So they don't contradict because I selected only one of them, here is 1. And here I selected the values for each of the variables. Only once. So one solution for anything. So if I can solve this problem, I can solve the satisfiability problem because I know which one I chose. Did I choose this one? If I chose this one, then not xi. If I chose that one, then xi. So I determine the value for each variable as the answer to this problem. If I have the solution, it will give me the answer to satisfiability problem. If I don't have solution, then the satisfiability problem doesn't have solutions. So these are the claims. If the set problem has solution, then subset sum problem as we defined is also solvable. And if it is solvable, then the subset sum defined by the formula phi is solvable. So it means that we have the SAT problem solvable. So if we solve the subset sum, we find the solution to SAT. If SAT can be solved, subset sum finds the solution. So this one is trickier, yes? Do you want to try it as well? Okay. Let's try that. So we have this formula already. Let's write what we get in this case. Okay. So W's, so we have m clauses and n variables. So m is equal to 3, n is equal to 2, we have only 2 variables, and k. So k1 is 2, k2 is 2, and k3 is 2. We have only 2 of them, yes? So B is the maximum of all those keys, which is 2. Now, we will write W1. So W1 is equal to B to the power of 1, which is 2, plus the sum for all j's. I have 3 clauses, so I raise b to the power of n plus j if xi is the variable in Cj. So if x is the variable in the first clause, it is variable in the first clause. So it will be 2 to the power of n plus 1. Next, x is the variable in the second clause, so it will be 2 to the power of 2 plus 2. But x is not a variable in the third clause. So that's all. So we'll have 2 plus 2 power of 3, 2 power of 4. Next, W2 will be about y, because it is x2. The second variable, which is y. So it will be 2 to the power of 2 plus, it is the variable in the first clause, so it will be 2 to the power of 2 plus 1. Then it will be 2 to the power of 2 plus 3, because it is not present in the second clause. So I'll have 2 to the power of 2, 2 to the power of 3, and 2 to the power of 5. Now, next W. I plus n, yes? So 1 plus 2 is 3. Do I have not x? Yes, I have not x. So it will be 2 to the power of 1 plus, I have not x only in the third one. So 2 to the power of 2 plus 3. 2 to the 5th. Now, W4 is about y. So I have 2 to the power of 2 plus, where is not y? The second place. So 2 to the power of 2, 2 to the power of 4. Now, big W. So sum of bi's, I from 1 to n, I have 2. So it's 2 to the power of 1 plus 2 to the power of 2. Plus this thing, kj, which is 2, times n plus j, which is 2 power 3, 2 power 4, 2 to power 5. So what is big W? It's 2 to the power of 1, 2 to the power of 2, plus 2 to the power of 4, 2 to the power of 5, 2 to the power of 6. So I need to match this sum using only those 3 values. And I see them, so I need to write this like 1. So if I choose these 2, I will have 2 to the power of 1, W1, plus W2. Plus 2 to the power of 2, then twice 2 to the power of 3, and I have 2 to the power of 4, 2 to the power of 5. Do I have enough? N times. Yes, N times indeed. Yeah. It should be matching. Okay. So it matched here, but didn't match here, yes? Somehow. Okay. Maybe we need it +1 or not. Let me see if I have +1. No. Okay. I think this is the problem. So W1 plus W2 should have matched this. Yeah, it didn't match. Somehow. Yeah, maybe something wrong with the formula. No, I calculated this correct. This one was correct. So if I just add W3 and W4, I don't have the answer, yes? Because I will have twice what I have 2 to the power 4, 2 to the power 5. I will not have 2 to the power 6. So that one is missing. But here I have twice them and once not that one. Okay, I will double check and tell you next time. So this one, again, the last one. Set partition problem. So given the set of S of n numbers, break S into two subsets with the same sum value. So you are given some numbers, and you want to divide it on two sets, such that if you put them on the scales, they will be having equal weight. Which is a very easy problem to translate to the previous problem. So the subsets sum is very easily translated to this problem. So what we have, we need to match these numbers, yes? So subset sum is reduced to set partition. Let us have the subset sum problem with n integers and target sum of w. The total sum of all numbers is t. We can easily calculate the total number. It is not hard problem, it is the polynomial time. We can calculate the sum of all numbers in linear time. Then we add a new number, twice w minus t. So what is the sum of all numbers now? So the sum was t, and now we add twice w minus t. Yes. So if I now order to divide this set in two parts, that each of them has the same value, each of them will have value of w. But this is not the input we had. We had input with n numbers, but we solved the problem for n plus 1 number. Yes? However, how many numbers did we add? 1. How many partitions do we have? No. 2. We have 1 subset that has sum of w and another subset that has the sum of w. Yes? So we have 2 subsets that are not the same, they do not intersect. All of them have some w. This one w, this one w. And number we added is only 1, can be either here or here. So we disregard the another subset where we have added number. So we have twice w minus t here. Then we throw away this and look at that one. Here we don't have our new number, and the sum of those numbers is equal to w. So this is the answer. Okay. let's show this. This one is very easy. Let's show this. Okay. Let's write it. So we have. Let me write the numbers. Okay. Those are the numbers. So we have the numbers. And we have W, which is 16. Let's say that we are targeting at finding 16. So let's sum up all the numbers. So T is the sum of the numbers. 3 minus 1 plus 2 plus 7 plus 5 minus 2 plus 8. 2 plus 8, 10. 3 plus 7, 10. It is 20. So these are 20. Then 5 minus 2 minus 1 will be 2, 22. Yes? So now I multiply W by 2. It will be 32 minus 22, which is 10. So I add this number. I will have 3 minus 1, 2, 7, 5 minus 2, 8, 10. Now I want to split them into two halves that have the same sum. So the sum will be 16. Because I added the number. So the sum will be 16. So what can I do? Let's select the largest number. It can be only on one place, so 10. How much I need? 6. So I can have 7 and minus 1. Yes? Yes. And the rest goes to the left. So 3, 2, 5, minus 2, 8. So 10, 18, 16. Yes. So this is the answer. So let's take a look here. So 3, 2, minus 2, 5, and 8. This is the answer.
Can you change Y? I mean W.
Yes? Because it will change this number. So when you change W, it will change this number, and everything is okay.
Should we get still the same answer?
No. The answer will change because